something that I want to make clear, clarify, okay, and something that I want to add on as well about the vertical circular motion and the horizontal circular motion. Now, next week we will enter the gravity. So today we'll finish up the circular, then next week we'll go to gravity. Okay, about the vertical circular motion. Vertical circular motion. Typical examples would be an object tied to a string and it's allowed to move around this vertical circle. So if you're dealing with strings, then we have tension, okay? The object is here, we have mg, we have tension. Let's call this point A. Okay, we pick a few points on the circles and we derive the formula for each point because the calculation depends on which position it is in the vertical circle. So at point A, where is the centripetal force? Now, so far we have understood that centripetal force is necessary to have a circular motion. So whenever there's circular motion, there must be some centripetal force. Where is the centripetal force? Is it found in the diagram? Now remember that whenever we draw the force diagram, right, we don't show the centripetal force. So meaning that the centripetal force is not shown in the diagram. What is shown in the diagram is the individual forces, the reaction, the tension, the weight. Because the centripetal force is actually a resultant force. Okay, it is a net force. So you don't see it in diagram, but we can calculate it. The resultant force, that means we take Fc, centripetal force, equals to T minus mg, okay? T minus mg. So you can kind of expand this, mv squared over r equals to T minus mg. So we have T mv squared over r plus mg at this bottommost point here. Okay, then we pick somewhere here. Okay, at this position, let's call it position, okay, position B. Again, we have tension inward, but the mg is vertical downward, right? Vertical downward. What is the angle that it makes here? If we count from this one angle, that means the angle is the same as this one. And it is the same as, if I extend this, same as this one. Okay, the cross angle. Now then we can do another derivation for this, which is centripetal force, again, is the net force equals to T minus mg cos theta. Okay, this is at this position, position B. The next one, which is at the tangent, the mg is tangential to the circumference. Here we have our mg, our tension. Now, if the mg is tangential to the circumference, right, that means that it is irrelevant. The mg is downward, tension is inward, so it's irrelevant to this one. So here my resultant force is just the tension. Centripetal force equals to resultant force. Let's call this point C. So I can write it as T equals to mv squared over r. And the last point that we take, which is at the top of the circle. Oops. Join this one. Okay, again, my tension invert, but the mg also same direction, downward. So resultant force at point D, Fc equals to mg plus tension. So mv squared equals to mg plus tension. Okay, so at the top, I can write it as tension mv squared over r minus mg. So all this formula you need to know. This one, depending on the calculation, if question asks about at this bottommost point, then we use this formula. At the side, we use a different formula, and at whatever angle, we use this one over here. Okay. Now, the thing is, at the top, the tension is the minimum. Okay, because here we can see mv squared over r minus mg, and here is v plus. At the bottom is where tension is the maximum. So usually the string, if it were to snap, it will snap at the bottom point here. Okay, and also because the tension is smallest on top, what happened to the velocity? From the formula here, we can see that this is a constant. This is a constant, this is a constant. So a variable here is the velocity, right? The v is the what? What velocity is that? Linear velocity, the tangential velocity, the linear velocity. The linear velocity, right, is different from here on top and at the bottom, because it's affected by the tension, right? Since the tension is different, then the linear velocity would be different. Okay, but understand that we are dealing with uniform circular motion. Uniform circular motion. That means, what is uniform? Our what do we call that? Our angular velocity. Okay, our angular velocity is actually the one that is constant. Okay, but the linear velocity depends at the positions for a vertical circle, right? So here we can calculate the speed at the top. Now, the speed, we know that for speed to increase, the tension increase, right? Because tension proportional to the square of v. So if I want to find what is the minimum velocity to sustain in a vertical circle, the minimum velocity, meaning that I want to drop this v, or I want to decrease the value of tension. Okay, first let's get the equation of v. We can write it as, I make the v as the subject, I get v squared equals to, okay, if you do the algebra, you get t plus mg over r over m. Okay, this is the equation to find velocity, linear velocity, and it depends on, all these are constant, but it depends on the tension here. If I want to find the minimum velocity to sustain this vertical circle, then my tension has to be minimum as well. Tension minimum. Okay, what is the value? What is the minimum value of tension? 0, right? 0. So t equals to 0 at the top. Okay, if t equals to 0, then we can say v squared, use blue colors, v squared equals to mg r over m, cross, we have v equals to square root gr, and box this. This formula is for you to calculate the minimum velocity, which is the velocity at the top. Now, at the top, right, not always the tension is 0, depending on how fast is the object moving. Okay, if the object is moving at this v, then you know the tension is 0. Okay, the tension is not necessarily has to be 0 at the top. Sometimes it has value, depend on how fast, what is the velocity of the object up there. This formula only allows you to calculate what is the lowest speed that it needs to be moving at to sustain this vertical motion. Okay, so understand that the vertical circular motion, right, the tension is not the only force that gives the centripetal force. It is not the only force that produces the centripetal force, because mg is also part of the component. All the point in the circle, at point A, at point B, at point D, mg is related, because mg has its radial component. We said that mg has radial component. Oops, radial component. That means anything that is pointing to the center, like the tension is always pointing to the center, right? So it's a radial component. So mg also has its radial component over here, here, here. except 2 points, which is point C, where mg is completely irrelevant, okay, because there's no radial component here. It's just tangent, it's all tangential, right? And also there's another point, the opposite here, where mg is also tangential here, mg. Okay, so mg and tension, both of the forces, and the result of these two forces is the centripetal force. It's not just the tension. Okay, and also if talk about the value of the tension moving from A to D. Let's say I swing the object from bottom to the top, meaning that the object moves from A to B to C and to D. What happened to the value of the tension? So you know at the bottom is the biggest, right? When it swings to C, what happened to the tension? Decreases, right? Decreases. And from C to D also decreases. So if you swing from A to D, the change in the magnitude of the tension decreases. And you swing back down, again, the magnitude increases. Okay, so if you were to kind of like draw the shape of the graph, it's like we have like angle and then tension value, you get something like this. Decreases, minimum, and then increases. Okay, this is when it reaches the top of the circle. Here is the bottom of the circle. Here is bottom, is bottom. This shows how the value of tension varies when you swing it like this. Okay, that is the tension. So same with the speed. The speed minimum is at the top and maximum would be at the bottom. Okay, so these are the things that to take note of, because sometimes the question will ask you, okay, where is it moving the fastest? Something like that. So Vmax would be at the bottom, V minimum here, simply because of the tension value is different. We look at one example, okay? Let's say I swing an object in a vertical circular motion having a linear velocity of 6 meters per second, 0.10 kg. Okay, calculate the tension T. Here is at the top of the circle. So which one do I use? At the top of the circle, I know that the tension, there's an mg here, T plus mg, right, equals to centripetal force. So T equals to mv squared over r minus mg. Then I put in the values now. 0.106 squared over radius. Okay, radius, let's take 0.50 meter. Okay, at the top, 0.50 meter minus 9.8, approximate to 6.2 Newton. Okay, so say you want to calculate the speed. What's the speed at this position? The minimum speed is 6 meters per second the minimum speed? No, right? It's not the minimum speed. How do you know? Because you have tension, right? Your tension is 6.2 Newton at the top. It is not 0. Your tension is 6.2. So meaning that 6 meters per second is not the minimum velocity. Okay, you can calculate the minimum velocity. V minimum equals to square root of GR. Get it from here. And we have, okay, I'll just take 10, easy. Okay, 0.5, that is 5 meters per second, approximate. Okay, so 5 meters per second. Minimum velocity is when tension equals to 0. The same is true for reaction. Other similar examples are like we discussed last time, the car moving in a closed, in a loop, in a vertical loop. Okay, it's like the loop. So car here, mg. Instead of tension, then we use reaction. Up here, mg down, and reaction also down. Concept is similar, just different applications. Or it could be like crossing a bridge, for example. For example, like a car crosses a bridge that has a circular path, circular surface. So like this. Where's my mg? Downward. How about my reaction? Upward. Okay, from the surface upward. The only difference is that the direction of the reaction, this one is upward. So you need a little bit of adjustment to your formula, right? So this would be the centripetal force would be the mg minus the reaction. Minus the reaction, and then you can get reaction equals to mg minus the fc, and very crowded here. Let me write it here. R equals to mg minus mv squared over r. Reaction. Because when it crosses this circle, you can think of it as if it was moving in like a vertical circle, okay, at the top here. Same concept, different applications. Right, you can take down, and I will go to the next slide. That is all for vertical. Next one, we'll look at horizontal circle. Okay. Horizontal circle. Swinging a ball horizontally. Okay, along a horizontal plane. Now, the only difference is the weight component. The difference between the vertical circle and the horizontal circle is the weight component. The weight component for a horizontal circle is always downward, meaning that regardless of the pointer, where is it in the circle, is always irrelevant because the tension is radial and the weight is downward. Okay, where is our linear velocity? Our linear velocity is tangential in this direction, v, and when it reaches here, then v. Okay, so think of it like I spin it horizontally like this. Mg is always not related. So that means, what is my resultant force? Resultant force is just from the tension. There's no surface, there's no friction, nothing. So just tension. That means tension is the centripetal force. Tension is Fc. It is the net force. So T equals to Fc equals to mv squared over r, or you can do the other one, the mr angular velocity squared. And also, typical examples, typical questions asked is that they often like to combine this with Hooke's law. Okay, so what you learn in Hooke's law, the tension here can be calculated using Hooke's law. So they give you the spring constant, okay, and they give the extension, find the tension here. So you can find it using the Hooke's law. Tension can also be found by Hooke's law. So tension equals to force equals to kx. Okay, so for example, they ask you to calculate the linear velocity from given the spring constant and the extension of the spring. When you swing it, you can get kx equals to mv squared over r. This is my centripetal, and this is my tension. Okay. Kx equals to mv squared over r, then you can find the velocity. Okay, and then third point to take note is talking about the work done. Is there any work done? What do you think? Work done by definition is force in the direction of displacement, in the direction of motion, right? So if the object is moving in a circle, then is it work done? Is there any work done? Force is the centripetal force, which is pointing towards the center, correct? That is my force direction, pointing towards the center. But where is it moving? It's moving in the tangential direction, the linear velocity. Okay, but you say, how about the angular velocity? The angular velocity, okay, is not where the particle is moving. Understand that. Angular velocity does not mean that the particle is moving in that direction. Particle is moving in the tangential direction. Okay, angular velocity is just another component, and it has its direction that we discussed in the last week, right? What is the direction of the angular components? So work done, we know that force is radial, but the motion is tangential. So our work done is 0. No work done. Even though the object is moving in a circle, regardless of how fast it's moving, it's still not doing any work. Same with the rotation of the Earth. The rotation of the Earth or the rotation of the moon around the Earth, there's no work done on the moon because the gravitational force asks the moon to come here, come towards the Earth. But due to whatever reason, the moon keeps on orbiting around it. It's not doing what the force asks. So there's no work done. Okay, because there's no motion in that direction of the force. All right, so next one is, how about the momentum? Momentum, does it change or does it same? Is it the same or is it changes? Momentum changes. Momentum changes is because of the velocity. Versus of v. You have momentum equals to mv, right? So v changes because of the direction. The magnitude is the same. That means speed is the same. Speed is the same for a horizontal circular motion, but the velocity is different because of the direction changes. And sometimes also question will ask, how about the kinetic energy? Kinetic energy, okay, kinetic energy is constant, right? Because kinetic energy half mv squared. This is speed, because kinetic energy is actually a scalar quantity. It has no direction. So since we are not dealing with directions, then the speed is the same, kinetic energy is constant. Example, I have a rotating disc where I put two objects with the same mass. One, I put it at a distance from the axis d. Another one, I put it, let's say, at the edge, which is 4 times the distance, 4 times the radius. This is x, this is y. I spin it, this one with a constant angular velocity. Find the ratio of Vy to Vx. I want to find the ratio of the initial, sorry, I'm going to find the ratio of linear velocity of y to the linear velocity of x. Now, first thing to know is what are the equations that we can relate with the v and the angular velocities. So we have v equals to rw, r omega, right? Okay, v equals to r omega. Now, what is the omega? You see, the two objects is placed, let's say this placed in one line here. They start here. Is the omega, is the angular velocity the same or different between these two objects? Is it the same? Huh? Which one has higher angular velocity? Which one has lower? Or is it the same? Angular velocity, angle over time. Okay, so it's like how much time to do one revolution. You place the two objects here after one round. The angle are the same. The time it takes to come back also the same. So meaning that both objects having the same angular velocity. Okay, they take the same time to go one round because they are on the same disk. Yeah, so angular velocity is the same. So this is the same, which means that we know V would be proportional to R. Okay, we can do simple derivation here. We know that V proportional to R. Vx is equals to D. That is the closer one. And we know Vy equals to 4 times the distance. Okay, so what do we want here? We want ratio of Vy to Vx. That is 4D over D cross cross. We get 4. Velocity, linear velocity of y is 4 times the linear velocity of x. Here. A lot of questions they ask like this one. Those that involve algebraic, the moving thing, the ratio thing. Okay, a lot of times when you do the exercise, you realize that a lot of time they ask this. What is the ratio of this to this one? This one, if the distance is twice, then what happens to the velocity? All these kind of questions. Okay, the algebraic questions. What is sustaining the object in a circular motion? We don't have tension. Unlike this one, right? Unlike this one, we have tension. We don't have tension. We don't have. We have reaction, but reaction is upward. This is our reaction. That is our mg. What is giving the centripetal force? The friction. Okay, the friction is giving the centripetal force. So we have friction equals to centripetal force mv squared over r. Or we can do friction equals to mr omega squared. From here, omega is constant in this case. So the greater the radius, the greater the frictional force. The more friction you are going to need to sustain in this circle. So between the surface of these two objects, of course, there's this maximum friction allowed, right? So if you go above this maximum friction, then the object will be thrown off. Okay, so it's kind of like they can ask you if the maximum friction value F max is whatever value is this, calculate the maximum angular velocity that it can move. Okay, or if the maximum friction is given like this, then calculate what is the radius, maximum radius that it can move in this circular motion. What are other examples of horizontal circle? So we have the string one, the friction one, we have the rotation of the Earth, object rotating on the surface of the Earth. This one, only the force component is different. The mg would be pointing towards the center, and the reaction would be opposite to the mg. Okay, in the case of rotation on the surface of Earth, in one day, okay, what is the centripetal force? Fc is resultant, so mg minus r. In the case of a blank road surface, like this, or any object moving in a horizontal circle in a curved surface, okay, inside a curved surface. Okay, so the forces acting would be mg downward, and then we have the reaction normal to the surface here. Okay, so that it will be making an angle here. This one, many cases like this one, like the car moving on a curved blank road surface, or an airplane rolling to one side. Okay, a motorcyclist making a turn, it's all same this for the curved surface. So that would be the centripetal force would be R cos theta equals to mv squared over g. Okay, you can R sine theta equals to mg. You may have heard of this spinning drum. It's like this straight cylinder wall. Okay, and then they put object inside. They spin the drum and the object inside make this circular motion. Seems like this object defy gravity. Okay, so it's kind of like we have a spinning drum. You put any object inside, it could be a person, anything. Okay, you put a person in here, and then it can go in a horizontal circle without falling off. So this is also the same. What is happening here inside? Centripetal is still centripetal force that keeps the person in this circular motion. Okay, now how it works? Inside, like here, what are the forces that keep the person moving in a circle without falling? First, we have mg downward, because it's against is touching the surface at the back, right? So it's kind of like, it seems like the person is like clinging to the wall, it's like being pinned on the wall when it move in a circular motion. So we have a reaction force. We have a reaction force normal to the surface R. And also we must have a friction, because without the friction, it would just fall off. So we need a friction that overcome the weight mg, F here. Okay, just to prevent it sliding down, So we have three forces here, R, mg, and F. Okay, so we know that frictional force is equals to the coefficient times into the normal. This is the equation of friction. The coefficient is like a constant, okay, depending on what surface you are is in contact with another surface. And it also depends on the normal force. Because sometimes you realize when you press something against a surface very hard, right, it's difficult to slide it. So friction depends on the normal reaction as well. Coefficient times into the normal. So that means I can do like, if I want to keep the person from falling off, then the friction has to be equal to mg, right? That means coefficient times into normal reaction equals to mg, like this. Okay, now what force is giving the centripetal? The R. There's only one, right? R. No other forces. So R is equals to the centripetal, mv squared over R. Or I can use mw. Okay, we put the other equation, mr omega square. Okay, mr omega square, because I want to compare the angular velocity. That means if you want to keep the person moving in a circular motion, you need to spin the drum fast enough. You need to increase this angular velocity so that the reaction is high and so that you have high friction to balance the weight. You get a point? Okay, here I want to increase the angular velocity to increase the reaction and to increase the friction so that the friction balance with the weight and it is able to move in circle, so it won't fall off. How do I increase the angular velocity? I spin faster. I spin the drum faster. Okay, so you may have seen the same examples like the death wall. Okay, in the circus, people performing like stunts. Okay, all these motorcyclists, drivers of like small vehicles, they move in this circular wall inside, right? They call it the wall of death. Okay, how are they able to maintain in a circular motion without coming down? It's like the whole car is moving in, like, how do you say it? It's like not even, okay, this is the, I actually have a video. I want to show you the video. Okay, let's spend some time, watch some videos. Okay, so all these professionals, they are able to move in a circular motion, maintain, but of course it has to do some tricks. I have to adjust some forces, like the speed. The speed is very important because you have to move above a minimum speed. Otherwise, you just fall down. Okay, if you fall down, it's pretty shocking. Right? It might cause it might be lethal somewhere. Let me find the video first. Let's spend some time, watch some videos. Okay, let's see. Before we watch the video first, then we go to the physics stuff. Okay, we watch the video first, then we go to the concept behind it. The concept are almost similar to the horizontal circle. Still has to do with the centripetal force and friction and stuff. Okay, let me find the video real quick. Okay, found it. This one. Stop. This video it talks about like a lady. She rides the death wall, and she do a lot of stunt, in it. You see lah. Let me play the video first. Check the sound. If there's no sound, you should be seeing the windows pop up right now. So if you don't see anything, let me know on your end. Let me play and test the sound. Yeah, you might want to adjust your volume a bit. So I'll just leave my volume here. Give me a second. Okay, you should be seeing the screen with. Let me replay the video. Replay the video. Okay. Okay.
Clinging to the roof of a car, stuntwoman Pooja Rathod spins at breakneck speeds around a circular wall. Welcome to the Well of Death, India's gravity-defying stunt show.
श्योर मेरे साथ 4 बार एक्सीडेंट हो चुका है एक्चुअली बहुत से लोगों की जा भी चुकी है
Just one slip of the wheel could mean disaster for this team of daredevils. And 20-year-old Pooja puts her life on the line in the show where entry cost less than $1. One of the only stunt women in the country, Pooja and her team of 4 drivers stun the crowds at every performance. Despite the risk of falling, Pooja loves to show off by dangling fearlessly from her vehicles.
तो मेरे अंदर थोड़ी हिम्मत है मतलब पावर है इसलिए मुझे हिम्मत ज़्यादा है तो इसलिए मुझे अच्छा लगता है मैं अपने आप को इंडिपेंडेंट समझती हूँ मुझे नहीं लगता कि सारी लड़कियाँ कर सकती हैं
The spectacle of motorbikes and 800cc Maruti Suzuki hatchback cars spinning on the 25-foot-high walls draws crowds from all over the country and leaves many spectators awestruck.
ये 2 कपल का स्टंट में दोनों के एक अपने गलों में हाथ डाल के गाड़ियाँ चला रहे थे और यहाँ पे आने का एक्सपीरियंस बहुत बढ़िया है मेरा
जो मुझे लोग बाइक पे स्टंट करते हैं हाथ छोड़ के पैर ऊपर करते हैं वो सब मुझे बहुत अच्छा लगता है
The Daredevil team wear no safety gear, but Pooja explains the key to survival is maintaining concentration.
ऑडियंस में ज़रा भी ध्यान नहीं देती क्योंकि काम ऐसा है कि हमको कंटिन्यूस के ऊपर ध्यान देना पड़ता है
And the young driver has a secret trick to keep her nerves at bay.
लेकिन हनुमान चालीसा थोड़ा बहुत बोलती हूँ जब मैं स्टंट में ऐसा लगता ही नहीं मेरी हिम्मत भी बढ़ती है
Despite the danger, the brave beauty claims that the scary stunts are the only way for her to make a living.
हाँ बुरा भी था एक बार बहुत बुरा होता पैर टूट गया था हाथ टूट गया था फिर 3 बार जो हुआ उसमें मेरे एक्सीडेंट के बाद मुझे ऐसा लगा कि मुझे छोड़ देना चाहिए लेकिन मैं फिर भी नहीं छोड़ पाई बस ऐसे ही दिल से इतना लगाव है कुएं से इसलिए और मुझे बहुत अच्छा लगता है अगर कोई नीचे आके मुझे मतलब हाउस थैंक यू बोलते हैं तो मुझे बहुत अच्छा लगता है अपने आप के अंदर महसूस करती हूँ कि चलो मैं कुछ ऐसा कर रही हूँ कि जिसकी वजह से सबकी दिलों में मेरे लिए मोहब्बत है तो मैं बहुत बेटर फील करती हूँ
Okay. So how did they do it? What's the physics behind it? Okay, let's see. Let's go to the board. This one. Okay. Now, most importantly, how do they maintain in this circular motion is the speed. You see, this is the huge cylindrical wall. Okay, it's like a wooden cylinder, and then they are moving inside, right? It's inside and go round and round and round. Okay, what is happening here? Let's draw the forces. The forces is almost similar to the one just now. Okay, let's say this is our motorcyclist. It is our motorcyclist, and it's making like tilting to one side. Okay, what are the forces acting on it? First, we have friction with the wooden wall, F, and then we have mg, and also we have reaction, right? Normal reaction, normal to the surface here, R. So F must be equals to mg to keep it stay up. So mu R equals to mg And we have the R equals to centripetal force, mv squared over R. mg, okay, I put the R formula in. That means here we have R equals to mg over coefficient of friction. So put it in here, we have mg over u mu equals to mv squared over R. Cross, what do we get? G mu equals to v squared over R. You see, if you want to maintain in a circular motion, your speed v must be large so that your reaction is also high, that it equals to mg, right? So we discussed that. The reaction must be high so that the friction is large to balance the weight, right? How fast you should be moving at? You can actually calculate this. How fast you should be moving at to be in a circular motion. So from this formula here, I can calculate v squared equals to rg over coefficient of friction. That gives me v equals to square root of rg over coefficient of friction, like this. Okay, so what is the r, the g, and the mu? Typical values of this one would be 5 meter, the radius of this 5 meter away. So diameter would be 10 meter. And for coefficient of friction is roughly about 0.7. Okay, somewhere around that. Okay, then you can calculate v equals to square root of 5 meter into 9.81 divided by 0.7, and you get about 8.4 meter per second, which is not very fast. If you convert this one, it's hard to imagine meter per second. So let's convert it to kilometer per hour. Okay, this one, so if we convert to kilometer per hour, this would be divide 1,000 divided by 8.4 divided by 1,000 divide 1/100. Okay, so we have in kilometer and we have in hour. Solve this, we get about 30.2 kilometer per hour. This is the minimum speed you need to be able to achieve if you want to ride the wall of death. If you drop below this one, then things would be a disaster. Okay, we just fall off from how tall is it? Mentioned in the video, right? A few feet. Forgot already how tall is it. Okay, so it's not that fast. 30.2 kilometer per hour is not that fast. It's very slow. It's the same for like if your position, if the motorcyclist can also do like this. Not only must it tilt its body, you can do like straight also can. Same force, friction, mg, and reaction, r. Okay, like the car, like the vehicle, 2 wheels you can go on it, 4 wheels you can also go on it.